David Spear, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We've got a frame problem, which is a 2D equilibrium problem. We've got this two-member frame. ABC is a vertical and BD is this bent member. Those two members are connected by a pin at point B and supported at the bottom by pins at C and D. And we can see right off that makes it statically indeterminate. I've got 4 reactions at the bottom and I've only got 3 equations to solve for the whole frame, so I've got to break it into parts to solve it. I want to know what those reactions at C and D are, and I want to find the magnitude of the force on ABC at point B. So the procedures for all these is to do a free body diagram of the entire frame, solve for the reactions if possible. Sometimes you can solve for some of them, some all the time, and some all of them, and then sometimes none of them, like on most of the simple machine problems, which are very closely related to this. Anyway, then we break it into parts at the pins, break it up into several rigid bodies that are all in equilibrium. Do a free body diagram of each of the parts, and the key things there are to assume Newton's third law or equal and opposite forces at the pins where they're joined together, and then look for 2 force members, because that really helps us with our geometry and helps us simplify the solution. And then just do equilibrium on the parts and pieces. So the first step is to do a free body of the entire frame. And here it is over here. You can see that I've got the applied force of 260 pounds. I've got my member geometry. And here's my assumed reactions, replacing the pins at C and D with these reactions, X and Y at C and D. I can solve for some of them by doing a sum of moments, for instance, about D, point D. And here's the numbers, 100 pounds. I break the 260 pounds up. It's a 5, 12, 13, so I break it up into 100 pounds vertical and 240 pounds horizontal. Anyway, break that up. Those forces times their distances, the moments they create. And then CY, I'm summing moments about D, so I've got CY, CX intersects it, so it doesn't count, doesn't contribute to moment about D. Anyway, I can do the math there, and I get negative 1980 divided by 3 is what CY is equal to. That's negative 660 pounds. That means the negative sign means the opposite of what I assumed, which was up. So I've kind of put a little black head on that arrow in the other direction, because I want to look at the sum of the forces in the Y, and I want to make sure I know that that's down. Anyway, so I've got 100 up, 660 down from CY, and dy assumed up, so that makes it positive. It is like I assume it up, 560 pounds. But I can't solve for cx and dx because I only have one more equation, and that gives me sum of forces in the x, cx plus dx plus 240, the applied 240, makes cx is minus dx minus 240. That's all I know about it. But then I've got lots more equations if I break it into parts. Let's do a free body diagram of part BD, this bent member, because I've identified it as a 2-force member. Force only at 2 points on the member, and they have to be collinear. And so I may not know initially what the directions are, but I do know that they have to lie along a line connecting those 2 points where the forces are applied. That from the geometry is a 3, 4, 5 line, and so I know that the force at B, which I've resolved into just one force, and force at D, have to be equal and opposite and collinear. So from the member geometry, I know that that has to be a 3, 4, 5 relationship, just like the member geometry. And so I've solved for dy down up here. It's 560 pounds up. Well, that's 4/5 of the force in the member itself. So I can just say dy is 4/5 of d, the overall force, and that's equal to 560 pounds, which also happens to be equal to by. But anyway, d is then equal to this number, 560 times 5 divided by 4, 700 pounds. And I know the direction from this. It's got to be up, so dx has to be to the right. by has to be down, opposite dy, and bx has to be opposite dx, just by sum of forces on the member. Therefore, I can say that dx is equal to, looking at it as the dx is the force to the left, it's negative 3/5 of that overall force in the member at d, 700, so it's 420 pounds to the left. Kind of knew that from my member geometry anyway. Therefore, the force B has to be equal to the force D, and therefore B is also 700 pounds. That's one of the things I wanted to solve for, the magnitude of the force on ABC at point B. Now I need to finish up and solve for my reactions at CX and DX. I go to member F, a free body diagram of member ABC. Here's the applied forces. I assumed, or not I assumed, I figured out that B has to be in this direction, down and to the right at point B on member BD. Therefore, it has to be equal and opposite, I'm going by this rule, Newton's third law, on member ABC. So I put it on there like that. I know its components because it's a two-force member, 420 and 560. And then I've got a pretty easy solution for the sum of forces in X. Negative 2, or it's 240 positive up here at this applied force, negative 420 from BX. CX equals 180 pounds to the right. A lot of these, all these frame and simple machine problems, I can check it with, I'm going to have extra equations so I can look at the entire frame, put the forces on there, and I see that in the X direction I have from CX 180 to the right, DX 420 to the left, the applied force is 240 to the right in the X direction, so that's equal to 0. Look at the Y forces. I figured 100 up here at the applied. CY I figured earlier 660 down, and DY I figured 560 up, so that checks also.